Here in Lecture 9, we will begin our study of the evolution of quantitative traits. The theme is often described as polygenes and the environment. Most ecologically important quantitative traits, which are often abbreviated QTs, vary, and the subject is variation. Distributions of trait values are often unimodal and approximately normal in shape. Offspring and parents are correlated, but not perfectly, and those correlations are a major object of study. Why does this happen? In a nutshell, it's that there are independent contributions to the trait values by genotypes at many loci throughout the genome, and also by random environmental influences. And our theory attempts and succeeds in modeling both of those sources of variation very successfully and simply. Why do we care? It's because the heritable part of the variation is the fuel of evolutionary change. The classic quantitative trait is human height or stature. It's been studied for something like 150 years quantitatively. This famous photograph is a living histogram of heights of women dressed in white sweatshirts and men dressed in black sweatshirts. I believe they're from an evolution class at the University of Connecticut. You can tell we're at UConn because there's the helmet and UConn written in the middle of this football field. The people are lined up in columns corresponding to 1-inch increments in height. The heights are indicated at the front, and you can just count up how many are in each height category. Heron and Freeman have turned it into a pair of histograms in the textbook, which I've shown at the upper right-hand side of the figure there. So what is a QT, a quantitative trait? It's absolutely anything that you can measure on a scale that has units of some kind. This is a bit unsettling to beginners, but in fact, you can invent new quantitative traits whenever you want, as long as you can satisfy this condition that it does vary in a way that makes sense to measure with a scale of some kind. Examples abound. Morphology, of course, like human stature, so the sizes and shapes of anything. The beak depths of Darwin's finches are perhaps the number 2 classic quantitative trait. Physiology is full of them. Pressures, temperatures, rates of anything, you name it, you can turn those into quantitative traits. And performances of other kinds. For example, swimming or running speed. Here's some data from the textbook on swimming speeds of men and women in some kind of event. Puzzle solving, IQ tests shown here are of sort of a puzzle solving thing. Here's a scale, a principal components analysis of paper and pencil test performances that are used to invent a scheme for measuring what people like to call intelligence. And of course, fitness. At the end of the day, fitness itself, number of seeds produced, surviving offspring, however you want to try to measure, quantify fitness, if it's on a scale of some kind like that, then it can be a quantitative trait, and it is inherently important because it's what natural selection is attempting, as it were, to maximize. We obsess about variances in this subject because they directly measure, and they turn out to be the natural measure, of a population's diversity of trait values. They'll frequently be represented abstractly by X or Y, some variable that may take on different values of the scale of measurement that's being used to describe the states of the trait that are present in the population. The variance may be denoted a number of different ways. We will use V of X, like this first form on the left here, or V sub X, which is a little simpler, or sometimes sigma squared sub X. Sigma squared is an old way of referring to the variance. Its square root sigma, without the superscript 2, is the standard deviation. And what is the variance? As we've mentioned before, it's the average squared deviation of the trait values in their units of X, whatever those are, from the mean for a given population or sample from a population, and we'll sometimes denote the mean as M sub X, the mean of X. So what's the mean of this distribution? Let's practice up on calculating variances, because that's going to be important. So this is just a little histogram. Each of these squares is one observation. We had this as a clicker question in a previous year, but we'll just step through it now. But let's calculate it. You know how to do it the grade school way. You just add up all the observations, which are 1. Right, this individual has a value of 1, and then 2 and 2. There are 2 of those. Then 3 and 3 and 3, 4 and 4, and 5. It's a total of 9 observations, so we'll divide that sum by 9. That's 27 over 9, which is 3. But of course, you could just have looked at the distribution and seen that, because it is perfectly symmetrical. And 3 is in the middle, and also, as it happens, the most abundant measurement class. Another way that's often more elegant to estimate the variance, to estimate the mean, is to multiply each of the trait values that occurs in the sample by its fraction of the example, of the sample. So that would be 1, which occurs 1 time in 9, by 1/9, 2, which occurs twice, times 2/9, 3, which occurs 3/9 of the time, 4, which occurs 2/9 of the time, and 5, which occurs 1/9. Do all those multiplications and additions, and you also get exactly 3, which is the correct answer. Now, what are the squared deviations? They're just the differences from the mean, which we just established is 3. Right, so here's 3. So the squared deviation contributed by this first observation with a value of 1 is 2 units. That's the difference between 1 and 3 squared. So that's 4. 1 minus 3 squared is minus 2 squared, which is plus 4. Then the 2's contribute 1 squared unit of observation each, because they differ from the mean by 1. 1 squared or minus 1 squared is 1, and so on. The ones in the middle, the most common ones, contribute nothing to the squared deviations because they're sitting on the mean. 3 minus 3 is zip, which squared is 0. Then 4 minus 3 is 1 squared for 1, and the 5 then contributes 2 squared again for 4. Okay, so the squared deviations are 4, 1, 0, 1, and 4. The mean squared deviation is just all those 9 squared deviations added up and divided by 9. 12 over 9 it is, which is 1 1/3. Or we can do it the same way as the fractions of the sample that have a given value. 2/9 are 4, 4/9 are 1, 3/9 are 0. That's 12 over 9 again, 4/3, which is 1 1/3. So here's another distribution, similar to, but not the same as the last. This was a clicker question. What's the mean of it? We expect you can get that just by looking. it's pretty obviously 5 is the right answer. And what's the variance? The answers are 1 1/3, 2 1/3, and 3 1/3. A little thought, I hope, convinces you that even though these numbers are bigger, the scale of measurement is bigger, the mean is bigger, it's now 5, not 3, the variance has not changed. The variance is still 1 1/3, which is to say, where we placed the mean of the scale of measurement doesn't affect the variance. Now, what's the mean and variance of this one? It's just like that one, only it's missing the third individual with a value of 5. The mean is obviously the same as above, it's 5. The variance has the same sum of squares, which was 12, you may remember from the previous slide, because these ones contribute 0, but now there's one fewer item. There are 8 of them instead of 9, so we divide by 8, we're going to get 1 1/2. So that's the variance. This distribution has a slightly larger variance than that one because more of the observations are farther from the mean, hence the variance is greater. Most quantitative traits end up being distributed approximately normally if we have a large enough sample. Sometimes a transformation like taking a square root or a logarithm helps to make them more normal, but often they're pretty normal just as is, as raw counts. For example, of dermal ridges in fingerprints, which back before you and I were born were a major subject of study. This is a big sample of fingerprint patterns, all quantified for total number of dermal ridges, and notice they are all over the place with a well-defined mean of around 145 ridges, a standard deviation of around 40. Normal distributions are used in this business for reasons that will be even more obvious to you shortly. It turns out they are very natural. They occur, and we expect them to occur in nature constantly. And they're all the same is one reason for using them. If we subtract the mean from every observation, the mean is transformed to 0. So we can center the distribution of any set of observations on 0 just by subtracting the mean, which is just a number, from every observation. And then if we divide every observation by the standard deviation, the standard deviation, and the variance will become equal to 1. And when transformed in this simple way, all normal distributions are the same, and they have these lovely properties, like 68% of the area roughly is within plus or minus 1 standard deviation of the mean, 96% of the area is within plus or minus 2 standard deviations of the mean, and so on. That's the standard normal distribution. And what we learn from this exercise is that the units of measurement are always arbitrary. We'll get the same insights, the same answer to a scientific question, whether we measure lengths in millimeters or inches or furlongs or whatever. Doesn't matter. They will come out in the wash if we transform into standard units, in which, notice, the scale of measurement is itself a scale of variation. Using the standard deviation as a scale of measurement means we're using a ruler which has been adjusted so that around 68% of all the observations will be within about 1 unit of the mean. Okay, so let's stop here, take a break, and come back and develop the genetics and biology of the quantitative trait model that lets us understand evolution of quantitative traits and even predict how trait will respond to natural selection.